Imagine waking up tomorrow and discovering that YouTube, Gmail, Netflix, and your online banking app have just stopped working. No videos, no emails, no online payments. Within minutes, millions of businesses around the world would literally come to a complete standstill. Sounds impossible, right? But every single second, billions of us are streaming videos, making payments, and using AI, completely without thinking about what's happening behind the scenes. So how does Google Search deliver answers in a fraction of a second? The answer is cloud computing. It's like the electricity grid of our time. Instead of factories generating their own power, they just plug in. Businesses do the exact same thing with computing power today. But here's the really interesting part. Cloud computing isn't actually the cloud. So what is it really? Let's find out. Okay, let's dive into this. The very term cloud computing is honestly a massive misnomer. I mean, it makes us think of this weightless, invisible data just floating somewhere up in the sky, right? Well, we need to completely shatter that illusion right now. The cloud absolutely does not live in the atmosphere. The internet lives in massive, heavy, loud, and incredibly physical infrastructure. When a company decides to rent computing power from a provider like Google Cloud instead of buying their own servers, that data isn't in the ether. It has to sit on real, physical metal somewhere on Earth. To really wrap your head around this physical scale, just look at this number, 10 million. That represents the kilometers of terrestrial and subsea fiber optic cables connecting the globe. These cables are literally the backbone of the internet, resting right there on the ocean floor. And because it's physical infrastructure, it's vulnerable to real-world physical problems. Get this. Fishing vessels and ships just dragging their anchors cause a staggering 2/3 of all subsea cable faults? No way, right? It's wild to think that the high-speed digital world we rely on every single day is constantly dodging actual ship anchors at the bottom of the sea. So when those cables finally reach land, where do they go? Well, they connect to 43 global regions and 130 distinct zones around the world. This massive, decentralized footprint is entirely by design. By spreading workloads across isolated and redundant data center clusters across 6 continents, providers can deliver sub-millisecond response times to billions of users. Basically, this means the heavy-duty processing sits geographically close to you, making sure that the 4K video you stream or the AI prompt you submit feels absolutely instantaneous. And building these regions, the level of investment is just hard to fathom. We're talking a 5.5 billion euro data center program in Germany, a 600 million euro campus in the Netherlands. But it's not just about the buildings. It's about the sheer power required to run the whole shebang. The cloud relies on a massive, power-first physical energy strategy. With gigawatt-scale campuses now becoming the norm to handle advanced workloads, we're seeing multi-gigawatt energy collaborations, like the one with NextEra Energy, and massive multi-billion-dollar acquisitions of renewable power companies. The cloud isn't just digital infrastructure. It is fundamentally energy infrastructure. Now, inside these massive campuses and through those subsea cables, we have to squeeze out every single ounce of capacity. This brings us to the Google Optical Networking Engineering team. To predict capacity planning, they don't just guess. Actually, in their labs, they have dozens of spools of fiber daisy-chained together to physically replicate the global network. Using an optical spectrum analyzer, they pulse lasers to find the absolute highest signal-to-noise ratio, literally pushing 1.2 terabits per second of zeros and ones through the cable. It is raw physics, meaning digital engineering. And this brilliantly illustrates how this infrastructure actually handles your data, because not all routes through the internet are created equal. If we look at standard internet traffic, it uses what's called hot potato routing. Internet service providers hand off traffic to downstream networks as quickly as possible, like dropping a hot potato, which means more hops and higher latency. But premium tier routing? That uses cold potato routing. It keeps the traffic on a private, high-speed backbone for as long as humanly possible, only offloading it at the very last moment. The result is up to 1.4 times higher throughput. It's a real game changer. Now, with all this data flying around the globe, security inside these physical data centers is absolutely crucial. They operate using a zero-trust security model. Picture this. Inside a data center, you have tens of thousands of identical machines securely hosting data for thousands of different companies all at the same time. Zero trust means exactly what it sounds like. Absolutely no devices, no users, and no services are trusted by default, whether they're inside or outside the network. This ensures that even on shared physical hardware, your data is locked down and completely isolated. So we have the power, the cables, the routing, and the security. How do businesses actually use it? Well, this is where we transition from the physical hardware to the software layer. That raw infrastructure is transformed into core cloud services that businesses simply rent. First, you have Compute Engine, which provides scalable virtual machines.
Then cloud storage, offering secure, durable object storage. And finally, App Engine, a serverless hosting platform. It lets developers host apps without ever sweating over the underlying hardware, patches, or backups.
These foundational services have completely revolutionized development. A company doesn't need to order servers, wait weeks for delivery, and then rock them up in a noisy server room anymore. Nope, they just click a button, and the cloud dynamically provisions resources for massive batch jobs or instantly spins up flexible virtual machines exactly when they need them. Now, what's really interesting about this slide is seeing how all this compute and storage comes together for massive data analytics. Take a look at BigQuery's architecture here. Notice how compute and storage are completely separated. The system uses a cluster manager, which actually evolved from Borg, the precursor to Kubernetes, to run hundreds of thousands of jobs simultaneously. It pulls from durable storage that seamlessly scales to exabytes of data. The beauty here is you don't pay for expensive compute resources just to store your data. They work together, but they scale completely independently. And tying this decoupled architecture together is the Jupyter Network Fabric. The scale here is, well, it's truly mind-bending. Jupyter can now handle over 6 petabytes per second of data center bandwidth. Because of its open, traffic jam-free design, it can instantly route requests to any free port without messing with other traffic. It uses 40% less power, costs 30% less, and cuts downtime by a factor of 50. It is literally the high-efficiency nervous system of the modern data center. So we've explored the millions of miles of subsea cables, the gigawatt campuses, the petabyte networks, and the serverless databases. But what is driving the most intense demand for this global compute power today? The answer lies in the most demanding workloads we are seeing in 2026, generating photorealistic, cinematic AI video models. These models require massive, incredibly scalable, high-performance infrastructure just to process and generate pixels in real time. So, the crucial point is, choosing an AI video generator in 2026 is no longer about which model can simply make a clip move, because honestly, they all can now. Looking at this 2026 comparison data, the choice depends entirely on your specific creative use case. Are you looking for cinematic realism, granular creative control, or fast social media effects? The best model is entirely dictated by what you are trying to create, not just raw visual quality. Let's move to and see how this builds into specific strengths. This completely reshapes the creative landscape. For filmmakers, Google Veo 3.1 and Kling 3.0 are leading the pack, offering incredible 4K landscape and portrait output with true cinematic lighting. But say you're a marketer making ads. Runway's Gen 4.5 family is the favorite there because of its granular motion brush control and brand consistency. And for social media creators who need rapid iteration and stylized effects to stop the scroll, Pika remains the absolute leader. But perhaps the most fascinating leap forward is happening in the audio space. In 2026, native audio and synchronized dialogue have become much bigger differentiators than visual quality alone. Models like Kling 3.0 Omni and Veo 3.1 can now generate ambient sound, background music, and accurately lip-synced dialogue in 5 different languages, all inside a single generation pass. And remember, all of this real-time multimodal generation, it's only possible because of that immense, power-hungry cloud infrastructure we just walked through. Which brings us to a pretty profound realization. We started on the ocean floor.